Welcome to the deep dive. Today we're jumping into the world of white dwarfs.
Yeah, these fascinating stellar objects.
Exactly. Now, they aren't the big flashy stars. They're more like the final act for what, almost all stars, something
Yeah,
like 97%.
that's the number, yeah. They're the dense remnants left behind.
So think of this as your kind of fast track to understanding these really incredible cosmic leftovers.
Precisely. White dwarfs are basically what's left after stars like our sun, run out of fuel.
Mm-hmm.
They don't go supernova, not usually. They just puff off their outer layers.
Right.
And what's left is amazing.
Yeah.
Something with maybe the sun's mass, but squeezed down to the size of Earth.
The sun's mass and Earth size. That's
Yeah.
hard to even picture.
It really is. And inside, usually carbon or carbon and oxygen, sometimes helium for the lower mass ones.
Okay, so a star's worth of stuff packed unbelievably tight. Why should we, care so much about these dense little things? What's the big deal?
Well, they're super important. They're not just dead stars. They're like cosmic laboratories.
Laboratories? How so?
They tell us loads about how stars live and die, about matter under extreme pressure, degenerate matter. Plus, we use them to measure distances, figure out the age of parts of the galaxy,
Wow.
and even understand what happens to planets when their star, well, reaches this stage. So, yeah, fundamental to a lot of astrophysics.
Okay, so they're like a key to unlocking a whole bunch of cosmic secrets. Makes sense. Now, the source material mentions classifying them with this system of letters. DA, DB, DC. Can you break that down?
Sure, it might look a bit like alphabet soup at first,
A little bit.
but think of the D that just stands for degenerate dwarf. Then the next letter tells you the main thing you see in their light spectrum, their atmosphere, basically.
Ah, okay, their chemical signature.
Exactly. So Da means lots of hydrogen. Db, that's neutral helium. Dc is, well, pretty featureless, continuous spectrum.
Okay.
Do means ionized helium, helium that's lost an electron. DQ tells you there's carbon, and DZ means you're seeing metal lines.
Metals, like iron.
Yeah, heavier elements. So that D letter code is like a quick atmospheric report card.
Got it. Elemental fingerprints. Now, something else that jumped out was the temperature range for these DA types. 170,000 Kelvin down to like 4,500. That's huge.
It is, and that range is basically all about age. See, they're not making new heat through fusion anymore.
Right. They've run out of fuel.
Exactly. So they just cool down over billions and billions of years. They radiate away their leftover heat.
So a cooler one is an older one.
Generally, yes.
Hmm.
That's a pretty direct link. And what's really neat is that some of them actually pulsate as they cool.
Pulsate, like throb.
Kinda, yeah. The ZZ SETI stars, they're pulsating DA white dwarfs. And there are others, like GW Vir stars, which are pulsating DBs and DOs. These little wobbles give us clues about their insides.
Huh, stellar heartbeats. So their temperature is like a cosmic clock. That's pretty clever. Now, you mentioned they're common nearby, but tricky to spot further out. Why is that?
It all comes down to luminosity. They're just faint.
Intrinsically faint, you mean?
Exactly. Compared to a regular star, they don't put out much light. So while there are probably tons of them out there, we only really see the closer, brighter ones easily.
Which makes surveys hard.
Right. It's tough to get a complete picture at large distances.
Yeah.
But the nearby ones, they were good early targets for parallax measurements to figure out distances.
Ah, the old geometric trick. Speaking of finding them, it sounds like our catalog has grown massively from, what, just over 1,000 in the late 80s?
Yeah, McCook and Cyan's early catalog work was vital. 12,279 in 87.
Uh-huh.
Then up to about 2,200 by 99.
Mm-hmm.
The online version in 2016 hit 14,000.
And then things really took off.
Oh, yeah. Big surveys like the Sloan Digital Sky Survey, SDSS, their DR7 catalog alone listed something like 20,000 white dwarfs.
20,000? That's a huge jump. Gives us much better statistics, I guess.
Definitely. Suddenly, we had a much better handle on the different types and how common they are.
Okay, so we know what they are, how we label them, how we find them. Let's get into the really weird part, that density. Degenerate electron gas. What does that actually mean?
Right, okay. This is where physics gets really strange. In a normal star, fusion pushes outward, gravity pulls inward. Balance.
Okay.
But in white dwarf, fusion stopped. So gravity's still pulling.
Yeah,
What stops it collapsing entirely?
good question.
It's this thing called electron degeneracy pressure. It's quantum mechanics, basically.
Uh-oh.
Yeah. Think of like trying to shove way too many people into a tiny room. The electrons are packed so tight, and a rule called the Pauli exclusion principle says they can't all be in the same state in the same place.
Okay.
So they push back. They create this pressure that resists gravity, but the result is matter that's just unbelievably dense.
Like the source said, a sugar cube weighing millions of grams.
Exactly that kind of density, maybe 106 to 108 grams per cubic centimeter. It's wild.
Mind-bending. And this leads to that mass-radius relationship, the Chandrasekhar one.
Precisely. Back in the 1930s, Chandrasekhar worked out, theoretically, that for these degenerate objects, adding more mass actually makes them smaller.
Wait, more mass, smaller size?
Yeah. Totally the opposite of normal intuition.
Yeah.
And there's a limit, the Chandrasekhar limit, around 1.4 times the sun's mass.
Uh-huh.
If a white dwarf gets more massive than that, say by stealing matter from a companion star, the electron pressure can't hold it up anymore.
And then boom.
Often, yeah. It can trigger a type Ia supernova.
Mm-hmm.
But below that limit, more mass means a tighter squeeze, a smaller radius.
And this relationship, even if it was theoretical at first, it's super important.
Oh, hugely. It
Yeah.
underpins so much. We use it to understand how many white dwarfs there are at different masses, how bright they should be, which helps estimate distances like to globular clusters.
Okay.
And like we said, aging the galaxy's disk and halo by looking at how white dwarf populations have cooled. People even use it to test fundamental physics, see if constants have changed over time, or look for effects of dark matter.
Wow. That's a lot, writing on one counterintuitive relationship. Now, the source mentioned binary systems like Sirius and its companion Sirius B. How do they help us nail down the mass and size?
Binaries are fantastic tools for this. If you can see both stars orbiting, like with Sirius A and B.
Right, Sirius B is the white dwarf.
Exactly. You can measure how fast they're moving towards or away from us, their radial velocities. You watch their orbit. Then you use Kepler's laws.
The old planetary motion laws.
Yep, they work for stars too. That lets you calculate the individual masses. Then, if you know the distance maybe from parallax,
Uh-huh.
and you can figure out the white dwarf's temperature from its spectrum, you can combine all that to calculate its radius.
So Sirius, at only 2.6 parsecs away, with its 50-year orbit, was like a perfect test case.
It really was a prototype for figuring out these fundamental properties directly.
Okay. But getting these precise measurements is key, and you need lots of examples. The Hipparcos satellite, it could only see a few nearby ones.
Yeah, Hipparcos was great, but sensitivity was limited. It observed just 22 nearby white dwarfs. Not a huge sample for detailed studies.
But then came Gaia, and the promise of what, a 10-fold increase? 200,000 white dwarfs?
That's the expectation, yeah. Gaia is just a revolution for this field. It can see much fainter objects, much further out, maybe 100 parsecs or more, for a good sample.
And it measures positions and brightness incredibly accurately.
Unprecedentedly so.
Mm-hmm.
It's astrometry. The positions and movements in photometry, the brightness measurements are incredibly precise. That lets us calculate distances, proper motions, luminosities much better, which feeds directly into better mass and radius estimates for way more stars.
And the impact is already clear, over 100 papers by late 2020 using Gaia data just on white dwarfs. That's a flood.
It really is. Scientists are using Gaia data to test that mass-radius relation with way more data points, find new white dwarfs in binaries, even triples, discover white dwarfs with dusty disks around them, probably leftover planetary debris, find them in star clusters, trace their movements through the galaxy. It's huge.
Planetary debris disks.
Yeah.
Wow. Okay, so let's dig into some of those early Gaia results. The source mentions Jimenez Esteban et al. And their big sample within 100 parsecs. What did they find?
All right, that was a landmark study using Gaia DR2. They found over 73,000 candidates and, crucially, identified 8,555 within 100 parsecs. That's the largest, most complete volume-limited sample we'd ever had.
What did that local sample show?
It showed that, locally, the coolest white dwarfs under 8,000 Kelvin are the most common. They could pick out likely co-core ones, even some rarer one-core candidates, and they calculated the local space density, how many per cubic parsec.
Okay, and they saw something weird in the HR diagram.
Yeah, a strange split, a bifurcation when you plot brightness versus temperature for white dwarfs. It wasn't really predicted by the standard models. And they also found quite a few really massive ones, over 0.8 solar masses, where it wasn't immediately clear how they formed. Still a bit of a puzzle.
A cosmic mystery. Okay, and Fusil et al. Looked even fainter.
They did. Pushed out to magnitude 21, finding something like 260,000 candidates. They reckon they were finding about 85% of all the white dwarfs brighter than magnitude 20, especially away from the crowded plane of the galaxy. A huge catalog for population studies.
And Hollands et al. Focused really close in, just 20 parsecs.
Yep, zoomed right in on our immediate backyard. Found 139 systems, including 9 that were completely new discoveries. The closest of those new ones was just over 13 parsecs away. Their work refined that local space density number 2.
It's cool how these different teams slice the data differently nearby. Faint, super local, all adding pieces to the puzzle. And Kim et al. Looked at fast-moving ones, halo objects.
Exactly. Stars moving really fast across our line of sight are often members of the Milky Way's halo, this older, sort of spherical component of our galaxy. Kim's team cataloged over 500 white dwarf candidates that look like they belong to the halo based on their high speeds. That tells us about the galaxy's early history.
So Gaia isn't just about quantity, it's about finding the really interesting oddball ones, too. Tremblay and colleagues found some cool stuff within 40 parsecs.
Oh yeah, they followed up on Gaia candidates and confirmed 191 new white dwarfs nearby. The really exciting finds included the first ultra-cool DZ white dwarf, extremely cold, but still showing metal pollution.
Metals again.
Right. And they found others with multiple metals. One was really strong in iron and nickel, the best explanation. It recently ate a planetesimal, a small rocky body.
Whoa. Direct evidence of munching on planetary leftovers.
Pretty much. Like cosmic forensics, reading the chemical signature of a destroyed world in the star's atmosphere.
Incredible. Okay, what about these extremely low-mass ones Pellisoli's team found? Less than 0.3 solar masses. How do they even form?
Good question. A single star wouldn't evolve fast enough to become such a low-mass white dwarf within the age of the universe. They almost certainly form in binary systems.
Interactions with the companion.
Exactly. The companion strips away mass from the star before it can fully evolve, leaving behind these lightweight remnants. Pellisoli's team used Gaia to find a huge sample over 5,700 candidates.
Why are they so interesting?
Because theory predicts many of these systems, with 2 white dwarfs or a white dwarf and another star close together, will eventually merge due to losing energy via gravitational waves.
Gravitational waves. So these could be sources for detectors like LIGO and Virgo.
Potentially, yes. Future space-based detectors might pick up signals from these systems spiraling together. They're prime candidates.
Very cool. And lastly, Vincent et al. Looked north, found new pulsators.
Right. They combined Gaia data with ground-based observations focusing on the northern sky within 100 parsecs. They specifically looked for those ZZ Ceti stars, the pulsating DA white dwarfs.
And they found new ones.
They bagged 38 new ones, including 2 that are very rare, ultramassive pulsators. Studying those pulsations lets us probe the internal structure. Even for these really heavy white dwarfs, it's like stellar seismology.
Amazing. It really feels like we're in a golden age for understanding these objects, largely thanks to Gaia. So let's try and wrap this up. What are the key takeaways from this deep dive?
Well, I think we've seen white dwarfs are the destiny for most stars, including eventually our own sun. They're incredibly dense laboratories for extreme physics.
Right, the degenerate matter.
Yeah. Their classification tells us about their atmospheres, their cooling tells us their age, acting like cosmic clocks. They're common, but faint, so surveys like Gaia are absolutely crucial. We talked about the vital, if counterintuitive, mass-radius relationship and how binaries like Sirius help us measure mass and radius directly.
And the Gaia discoveries.
Exactly. Gaia's finding them in huge numbers, revealing population details, weird splits in diagrams, discovering polluted ones that ate planets, finding potential gravitational wave sources. The list goes on.
It really paints a picture of their importance. Stellar evolution, fundamental physics, galactic history.
Yeah.
All wrapped up in these tiny, dense embers.
Couldn't have said it better.
So, a final thought for you listening. As we find more of these, especially the really massive ones or those merging low-mass pairs, what else might they tell us? What secrets about how galaxies form or even about gravity itself are still locked away inside these stellar remnants? It's clear the study of white dwarfs is far from over. There's definitely more to uncover. Thanks for joining us on this deep dive.